my new friend Eric Obeng, and we're going to do a deep dive into a circuit board that Eric's working on. The goal here is that I will do my normal board analysis, and then this will be something that can be used by Eric and his followers to get a better idea of how to directly manage electromagnetic fields using a printed circuit board. So, Eric.
Yeah, great. All right, so the circuit I have here is a solar tracker. It's a system to control a solar panel to its positioning in the sky where it faces. So basically, it's supposed to chase the sun, and then so that we can have maximum output from the panel. It's supposed to drive a maximum of about 60-watt panel. So if I bring out the 3D view, we have just some basic stuff on it. Please, can you see my 3D viewer?
Not yet. I can just see the PC board flat design.
Okay, let me see. What about now? Can you see the 3D view?
There it is.
Yeah. So I have two drivers, motor drivers on it. Then it is IoT, so I have an ESP32 module on it. Then there is an FCDI chip, FC232 IC. Then I have, so I also do short open circuit voltage and short circuit current recording. And that's what I use this relay switches for. So basically, that is what this board is doing. There is also a micro Atmega 328 IC in here. Yeah, and it's a 4-layer board. The stack up is power ground. Let me go there. So the stack up is power. The top is power and signal. The two internal layers are ground, and the last layer is also power and signal. Yeah, so I'm going to show just the top layer. I don't know if there is something you can do from here.
Okay. That's a good start. The only other, I don't know if you're showing the ground flood, is one of my normal processes is to anything that's not being used for a signal or power boundary conductor is flooded with ground.
Yeah, I think.
Yes.
Yes, I have this there.
You're flooded ground. Yes.
Yes.
Okay.
Actually, the top layer is power and signal. So the ground pour is actually 5 volts.
Okay, that's one thing I would always change.
Okay.
One of the rules that I learned from Ralph is you don't route signals where you're not going to use them. And that especially applies to power, which is one of the conventions people have been following blindly forever, that they flood power. There's no real planar capacitance at all. And what you want to do is only connect the power island where there's something physically using that energy.
Okay.
So the boundaries for your 5-volt would be where the IC and capacitors are connected to it. And then the interconnects between the voltage regulator and these devices would just be routed as traces that are sized according to the amount of energy required. So if you need an amp, you'd need a fairly wide trace, but you don't want to flood the entire system with power, because what that does is enables those the waves that are associated with the 5 volts go places they don't need to be.
Yeah.
And that can cause problems. Whereas if you flood with ground, the you improve the Faraday cage that's helping to control the other fields that are across the board geometry.
Okay.
That's one thing.
That's
In fact, this is a common process of most of my customers, and I have to have them back off. They'll put, a whole plane of 3 volts, but you don't need it except in a small 2-inch square. So the rest of that area becomes either opened up for routing signals if needed, or it's much better to make that ground copper.
Wow. Okay. Great.
So these is exactly the things we can use as a way to determine a good process. The other thing I want to suggest is I can see places where there are traces close together.
Okay.
Just like in the middle of the board or any place that you have traces close together, if there's a way to spread them out and allow
Okay.
the ground flood, which is what this is going to change in to be able to go through them, that also helps improve signal integrity, reduce
Okay.
the impedance of those transmission lines, and increase the overall EMC performance of the system and
Okay.
the robustness from an ESD perspective. The whole idea is without having to spend any more money, you take the materials you're already buying and you use them more effectively.
Okay. Okay. Great. Wow. Okay. So.
And you'll, as we
Mhm.
continue on, you'll start to see the logic in this because, like you say, there are a lot of guidelines that are out there that were just, they weren't so bad they caused failures, but in today's world, they can reduce the effectiveness of the overall design.
Yeah.
And this makes this board a really good example of how we can make it better. And I see just another note in where you've got interspaced power and ground vias, you've used my waterfalls, and that's
Yeah.
excellent way to connect the dielectrics in the z-axis.
Yeah. Yeah.
Okay, so that would be the first suggestions based on
Okay.
looking at layer one, because this is my normal process. One layer at a time, I walk through the board to start establishing
Okay.
the foundation. So
Sure.
now let's look at layer two.
Okay. Layer 2. That's a ground plane.
Yeah, let's see it.
Yeah. So I'm showing it right now. Is the yellow? It's
Okay, and
yellow.
it's a solid ground plane. There's not
Solid ground.
multiple. Okay, that's a very good thing. So, when you're moving energy on the components that are using on the components on layer one, the energy is flowing in the dielectric between one and two.
Yeah.
That's the energy flow process. Okay, now let's look at layer three only. So you've decided to make this solid ground as well, correct?
Yes. Except when I there is this little break I put here because I didn't want to reroute some part of the board. So I had to just do this little break here, which I know is not good, but
It's underneath a component.
yes, it's underneath the component.
Okay, what's on layer one there is layer one.
Layer one is an IC.
With a
It's an
exposed pad, or what's under the IC on layer one?
just the space under the IC. There is no exposed pad on it. It's just right like under the body of the IC.
Okay, so you could conceivably put that on layer one. All right, let's think about that farther. Now let's look at four.
Okay.
And is four ground flood, or do you use some power in there as
It's
well?
also power flooded.
Right. So that would be what I would suggest is to where you need to have a lot of current flowing,
Okay.
like to the motor drivers and things, that
Yeah.
if you put those conductors on one and three, then you would have parallel dielectrics between one and two and three.
Okay.
And the nice thing about that is that they're automatically a paired dielectrics, and
Uh-huh.
that's what I call a triplet. When you have signal, ground, signal, the
Signal ground
when
signal.
you go
Okay.
from one to three, the the opening around the via connecting the two signal layers provides a connection between the dielectrics between one and two and three. So those are automatically good transmission lines. And
Okay.
when you use the um, copper on one and three that are basically the same copied. Then now you have two parallel dielectrics that you use to move the energy.
The
So
energy.
twice the capacity of what you were doing.
Yeah.
So
Yeah.
that would be one thing to look at doing, where you're moving the power around. Now, the real challenge in a 4-layer board is that if you go from 1 or 3 to layer 4, you must have a ground transition via next to the signal via or power via.
Okay.
The dielectrics, layer 4 is not connected to layer 2 if 2's the ground. And the dielectric between 4 and 3 is not connected to the dielectric between 1 and 2. So you have to give a z-axis connection for the dielectric between the top dielectric and the bottom dielectric.
Okay. Okay.
So this is where I've got a number of customers who've had failures because they didn't allow for that energy to move through the board stack between layers. You know, anything on layer 1 or 3, if you just drop a signal via to 4, then it has to find the nearest ground via somewhere. And if there's other signals in that space, then they will also be sharing that space. So it increases crosstalk.
Yeah.
And then because the volume of the space is higher, then you have a temporal distortion with that signal because it takes longer to fill that space between the signal via and the nearest ground via.
Yeah.
And then so you've distorted the signal in two ways. One, there's crosstalk, and two, there's a temporal distortion because of the extra time it takes to fill that space. So those are the kind of things. Actually, I was hoping that these were here so we could talk about the importance of this approach. So let's, if you zoom in into the middle of the board next to switch 2,
Switch 2. Okay.
just
Here.
above your cursor,
Yeah.
you can see there's two vias there together that are signals.
Yes.
Those are
Here.
coming.
Here.
Those are coming from layer 1.
Yes.
And
Yes.
so there's no. Now back out a little bit. And now look at all the signal vias that you show around the board. Where is the nearest ground via?
Wow.
Yes, that's exactly the thing that I
Yeah.
look for in designs. So every one of those signals has to find that ground via or one ground via, maybe the connector pin to the left. All those signals share that space because they don't know where to go.
Yeah.
So spread out, they try to find the nearest ground via, and so all these signals will have issues and crosstalk. Now, you know, granted that most of these signals are not switching very fast, and so they are still, the discontinuity is effectively lumped.
Yeah.
But the idea is that every time you fail to provide a transmission line that you designed, that it reduces the overall EMC behavior of the board. And
Yeah.
maybe it doesn't cause it to fail to function. And perhaps it even will still pass EMC. But if you're looking for a way to create a process and design guidelines that will be useful in every design, whether it be something switching in 10 milliseconds or something switching in 10 picoseconds, that the philosophy will be there to enable that type of design. And then the other thing would be to spread them out if possible, you know, and it's not necessary, but you know, the key is that with a board where you don't have a whole lot of routing needed, is you can definitely right now, because you do have 2 and 3 as ground planes, but we want to take advantage of that layer 3 to increase the capacity for where you're doing your power connections, is that underneath these and so, but you would only need to do that where you're routing the power.
Okay.
The DC power. The rest of that could still stay as ground plane, and that would provide a good transmission line for all the other signals on layer 4. And you just would have to be careful for how you do things on 4, where the power connections are. So, and you could pick and choose where you want to have this these paired dielectrics.
Okay.
Usually on the line where the connector, where the components are located, is the best place to have that. So that's why I was suggesting 1 and 3 for your parallel power
Okay.
conductors.
Okay.
And then on layer 4, you wouldn't need these connections that are on. Currently the way you have it, you have 2 transmission lines for the power, because you've got the same traces on 4 that you have on 1.
Yeah.
At this bottom right hand corner, for example. So that means that on the outer layers, you would have this side be flooded with ground, and then you would be using those inner dielectrics, because these are all through-hole connections, which makes it much easier than if they were surface mount.
Okay. Okay. Yeah. So let me ask this question. So the spacing. Sometimes I see people talking about 4H, the spacing between the traces. Some people talk about 4H, others say 2L. Sometimes I'm quite confused about it.
It really depends on the switching speed of the driver, and
Okay.
it goes to the rule, the square the distance rule. So
Okay.
the amount of energy coupled that's shared between any 2 conductors is reduced by the square of the distance. So if it's twice as far apart, it's 1/4 of the energy.
Yeah.
And I want to quickly discuss the idea of crosstalk. Crosstalk happens at the wavefront. So as you're switching energy back and forth. So what happens as the wavefront is moving, you have a changing E field.
Mm-hmm.
The changing E field will create a changing H field in the next conductor.
Yeah.
So that changing H field will then cause a changing E field in the next dielectric. And that's how the energy is coupled from signal to signal, because it's traveling in the space between the bottom of these traces, or on layer 4, the top of the trace, and the ground plane on 3. So the wave's traveling through there, but it's creating an H field in the signal trace, a changing H field. So that changing H field now will affect the space on either side to create a changing E field in those spaces, and then that will cause a changing H field in the next trace, which then causes there to be a changing E field in that signal space.
Yeah.
So it progresses. So the farther apart they are, the lower magnitude of that field that's being transmitted from place to place.
Okay.
And that's one of the reasons. So the spacing is really a function of the frequency of the switching event. So how aggressive that wavefront is. So the current density in the wavefront, the displacement current, is what causes all the evil. So as long as you have a good transmission line, meaning that this is always over a continuous ground plane,
Yeah.
you'll have most of the signal will be well behaved, and the only reason you start to worry about the separation distance is as you increase the frequency of the signal. So the dVdt versus the switching speed becomes an issue, because that current density in the displacement current increases as the switching speed increases, or the speed is increased. So the faster it switches, because it's all about current density per square centimeter.
Okay.
And a slower switching wave has a much larger wavefront. So the area of that is larger. So the current charge per cubic centimeter, or per square centimeter, is much less than if you have a very fast signal and the square area is much lower, but it's still the same amount of charge being changed. If it's a 5-volt signal and you're switching it in 10 milliseconds, the density of that displacement current is very low. But if you're switching a 5-volt signal in a nanosecond, then you have 1,000 times higher density of the displacement current in that square area. So that's where you start to get the energy moving more aggressively, because it's causing a more aggressive change in the magnetic field as this electric field moves through that space.
Wow.
So
Wow.
again, it's really simple, but
Yeah.
it's all clouded in confusion and magic. But the behavior of the electromagnetic fields is predictable and it's constant. It
Yeah.
always does the same thing. And the way it influences other signals around it, or the way it is propagated through the the system is a function of that, that energy. How much energy is in that wavefront per per time constant, per time
Yeah.
unit. So for these things, the improvements would be from the ground transition vias
Yeah.
and making sure that there's a continuous ground copper on the bottom, and that's some of the early changes I would suggest you make. The other
Okay.
thing is for components, uh,
Mm-hmm.
of you can't route under things that are replacing sections of copper. So you can't route, so you don't want to flood under resistors, diodes, transistors,
Okay.
switches, close, um, because you're really trying to keep the field that's in the dielectric, has to see those components.
Okay.
And and so if there's stuff underneath components, then they will be involved in that energy that you're trying to control, either with a resistor or a diode or a switch or a transistor. Um, so it's really starts to restrict the availability of routing space, which in the case of this type of application where you have the components we're looking at are on layer one, correct, at this point?
Yes, they only are one. Yes.
Yeah, so on layer one, things that you route underneath the components, but we're looking at the traces on four. So where you have anything under these components, you have to try to push them to layer three.
Any trace under a component should be moved, if I heard it
Well,
correctly.
ICs are not such a big deal depending on what the signal are, but things that replace that could be considered the switched conductor. If you remember some of the drawings that I did, there's two things that have to be constant. The continuous conductor is the connection between the power supply and the load. That's the return or ground. Next to
Okay.
that has to be a continuous dielectric, which is unbroken from the source of the energy to the load. And then that's bounded by the switched conductor, which starts out from the power, the power supply next to the ground. It gets to a voltage regulator or a switch or a
Okay.
diode, and that component is part of the switched conductor. So on the
Okay.
other, so that component needs to see the continuous dielectric.
Okay.
And then on the other side of the switched conductor, you pick up the field moving, and then you go to the next switched conductor where you still have to maintain that continuous flow of energy. Now the impact is again going to be depending on the switching speed of the wave, the device, and the
Okay.
amount of energy that you're trying to move.
Let's move.
So under this capacitor, the capacitor needs to see the dielectric between layer one and two. Pin
Okay.
one and two of the capacitor are the open bucket that's going to catch the field and store
Okay.
it. And this is where understanding the impedance is. You've got a larger impedance in the space between layer one and layer two as that
Mm-hmm.
energy moves through that dielectric. When it gets to the capacitor, it goes from an impedance of, even at best, it's 50, maybe less because you've got a wider conductor, 50 ohms. When you get to an electrolytic capacitor, you're looking at more like 500 milliohms. So it sees a
Wow.
1/10 the impedance. So it wants to go into that capacitor and fill it up before it goes any farther. So right
Okay.
now, the way this is with the routing underneath the capacitor, these signals are part of the energy movement from the 1 to 2 dielectric into the dielectric inside the capacitor.
Okay. Okay.
So that would be traces you want to push over to the other side of the capacitor.
Okay.
or else they're part of the power supply. So the waves that are going in and out of the capacitor, you've got a changing E field. It's going to cause a changing H field in these traces, which is going to affect the electric field that you're trying to move through there.
Okay. I think I understand. I
Yep.
understand. I understand. All right. So that means I can even try and move them away.
Yeah,
Just
put them on the other
big.
side or drop them down to layer 3.
Yeah. Okay.
But then but there's also, I see signal vias dropping some of these down to layer 4.
Yes.
You would need ground transition vias for those.
Yeah.
From 1 to 3, you don't need them, but when you go from 3 to 4 or 1 to 4, you need a ground transition via.
Okay, great.
So it looks like you're dropping down because you have to cross over these 2 vertical traces in the middle.
Yes, yes, yeah.
Yeah.
Wow. I think after this training, I'm going to keep this. I'll duplicate it and reroute it and then send it over. I'll put all the things you are saying together and put it to.
That's exactly the right thing. And if you can do A and B testing, I don't know if you've done any EMC testing on this design.
No,
You would
not.
be able to document exactly what impact this has.
Okay. Unfortunately, where I find myself, I can't do that.
Right, I understand that, but
Yeah.
and you may not be able to quantify the behavior because obviously this board functions, right?
Yeah.
You're able to drive your positioning system.
Yeah.
And then the other, so those are some of the basic things to do. I see you've got lots of stitching vias. Those don't really do anything for you.
Oh, okay.
It's one of those things everybody thinks it's a good idea to do, but
Okay.
if there's only one signal, having multiple vias with the same signal, whether these be ground or power, there's no field moving in that because it takes 2 different conductors to allow a field to exist. So between stitching power vias, there's no field, which is okay, but it's not necessary. It doesn't hurt anything, but it doesn't really add anything. A single row, if you're really trying to put a boundary to prevent edge radiation, which is a very real thing, doesn't really matter.
Oh, okay.
I see underneath this 3 ground silk screen, there's that's probably up in the upper left.
Upper left here.
Where it says 3 ground in the red and the white silk screen.
Here.
The grid to the right, where your cursor is now. So that's there because there's a thermal pad on a device, right? That's a power switch or a voltage regulator.
Yes, that's a 5-volt regulator, LM25. So the idea was to ground this, get this connected very well to the ground.
Right. So that's what my point was, is for thermal reasons, a massive ground vias to connect the ground copper is good. From a signal perspective, it doesn't do anything. So this is important for dispersing the kinetic energy.
Okay.
But doesn't do anything for the fields. So, but you have to do this quite often because you're trying to keep these parts from catching fire. Now, I see you've got AC relays on the left. Right?
They are actually
20.
Yeah, I have
You're
some
switching
relays.
AC?
No, it's DC. DC.
Oh, these are all just DC relays.
Yeah, they are DC relays.
Okay, so take a close look at the way the energy moves onto the board and from into the switching networks, and try to make sure that path is only as direct as possible.
Okay.
So that's where, when you're looking at changing the power floods, that you manage those so that you make the energy go where you need it to go.
Okay.
So where's the power input to the 5-volt? Is that a 12-volt input or
it's a 12-volt input?
Okay.
Coming from there. Okay, so coming from this battery connector
Okay.
here.
So let's walk through the power supply.
Okay. So it starts from here.
Yep.
Maybe I should turn on the ground and the fourth layer.
Right. Where are you routing the battery power on?
So it's at the base, mostly on the fourth layer, and there is actually a pour. I did some pouring the 12 volts over here, and I'm tapping it along. So battery actually comes in here.
So 1 and 2 are your battery inputs. So you're bringing it in, but you don't have this battery power on layer 1.
No, I don't have it on layer 1.
Okay, so it's coming into the board between layer 4 and layer 3 in that dielectric. So it comes from the wiring harness between these 2 pins, and then you're feeding it into the horizontal dielectric between 4 and 3. It goes over to the left, and what are those 2 components?
So this is
what are
I
those?
think it's a diode. Yeah, they are diodes, Schottky diodes.
Those are for reverse battery?
Yes. Let me see. Yeah, it's supposed to prevent reverse polarity, something like that.
Yeah, to protect the board from
Yes,
battery,
but
from somebody hooking the power up backwards.
Mhm.
So that's good.
Yeah.
And you don't have flood underneath them. So again, these guys are in series. They're the switched conductor. So it
Okay.
comes from the battery pin and the ground pin into the space between 4 and 3, goes to these diodes, which replace a piece of conductor. So it's in the space between the diode bodies and layer 3.
Okay.
And then it moves into the distribution of the protected battery and feeds this capacitor above right here. Okay.
Yeah.
So this capacitor, these capacitors, there's 2 on the right, it looks like, are on the top.
Yeah, they are on the top, but these 2 are for my solar panel, and these 2 are for the battery.
Okay. So I see that you have pin 1 of these is connected to what layer? Straight up to the top of the board?
Pin 1, as in of the capacitor.
Yeah, or they go right up to the top of the board?
No, everything is connected at the bottom. So maybe just the pin, the pad or the pin of the
Okay.
capacitor.
So these interleaved vias, but there's no, is there any other copper associated?
So
Those
the
are 5
interleaved
volt
via
vias.
5 volt and ground.
Right, no, so you don't need, those don't want to be in there. This is
Okay.
12 volt land. So you
Okay.
need to make sure that there's 12 volts. So that waterfall needs to really be associated with the battery, because you've got to get from the dielectric between 3 and 4 to the dielectric between 1 and 2.
Okay. This is not a 12 volt land. I
Right,
routed the 12 volts.
right.
So,
You don't want that in there at all.
okay. All right.
So because you really have to somehow get the energy from the bottom dielectric up
Okay.
to the top dielectric. And
Mm-hmm.
right now there's a lot of stuff in the way.
Okay.
So this is where you would want to have some even along that trace. If you put vias to a similar trace that's on layer 1, which you probably have flooded with 5 volts, is to
Yeah.
make that a parallel, make that copper on layer 1 that matches this copper on 4, puts a bunch of vias in that space along that trace, and next to it put ground vias. so that you have a z-axis path for the energy to move from the dielectric between 3 and 4 into the
Okay.
dielectric between 1 and 2, and then make sure there's nothing between the leads on layer 1 for these capacitors so that they see the dielectric between 1 and 2.
Okay. Okay.
You got to have their mouths open and touching the dielectric on layer 2, between layer
Okay.
1 and 2.
Okay, that's great. So the ones that I've highlighted, they are the 12 volts power. That's the
Yeah,
12 volt power coming from my battery.
yeah.
Yeah.
And then you've
Okay.
got a second power input from the solar cells. Is that
From
what
the
the
solar,
other?
yes.
Yeah, you want to do exactly the same thing there so that you can get the energy from the dielectric between 3 and 4 up to the dielectric between 1 and 2.
Okay. Okay.
And that needs to be a clean, open path.
Okay. But over here, my solar, the power on the solar is not actually coming to the top layer. It stays in the bottom layer.
Right, but
That,
then there's still no way to get to the capacitors that are on 1.
oh, okay.
That's what you're trying to do. You've got to get the energy from the space between 3 and 4 up
Okay.
to the space between 1 and 2.
Okay.
And there's no plumbing there. You're filling the basement to get the water to the first floor.
Okay. Wow. Right, 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 right. That's great.
So hopefully you're getting a feel for what the philosophy is, and starting to think in 3 dimensions in a context of plumbing.
Mm-hmm.
That you're designing the pathways for the field to move in.
Okay.
2 of the components of the 3 required for field management have to be continuous ground, continuous dielectric. The third component, which is the one you really are trying to design, is the switched component. But you
Okay.
need to be able to, without, from the load to the switch, to the source, that has to be an unbroken dielectric. If you can't
Okay.
see a continuous dielectric bounded on one side by ground from where the energy starts to where the energy is going, then you've got a discontinuity in the movement of that energy.
Okay.
And that reduces the effectiveness, because the higher the impedance of the transmission line, and every discontinuity is a reflection point. And the
Okay.
goal of a good design is to reduce the number of reflections it takes to move the energy from place to place.
Okay.
And that's done by increasing the capacity of the transmission line so the energy per wave cycle is higher. And that reduces the number of waves that have to happen, which reduces the number of opportunities for EMC issues. Because again, all evil happens at the wave front. So
Wow.
you make sure that the waves fronts are not going to cause problems by the design or impedance of the transmission line and the distance between the traces. And then you reduce the number of wave cycles, so the number of times the wave can cause problems is reduced to as few as possible.
I see. So that means that it's a good idea not to have copper pores under components like capacitors and
Right.
resistors.
Under components, you don't want a copper pore,
Okay.
because those components need to see the dielectric on the next layer. So if a
Okay.
component's on 1, it needs to see the dielectric between 1 and 2. If the
Okay.
component's on 4, it needs to see the dielectric between 3 and 4.
Okay.
They need to see that space, because you're trying to move the energy that's in the space horizontally into a component.
Mm-hmm. Wow.
Wherever field needs to move, you need to make sure there's nothing in there that will be affected by the movement of that energy. So
I see.
capacitors, resistors, diodes, everything you possibly can, you move things from underneath them. Now, in the
Okay.
case of this this trace, we're looking at 4 still. So this trace between the leads to the left, you know, let's look at the left-hand capacitor bank. There's a vertical trace there to the right of the.
Yeah, this one.
He's not in the dielectric that's connected to the capacitors.
Yeah.
If that was on layer 1, it would be a problem. On 4,
Okay.
as long as that's continuous ground on 3, it's not
Okay.
in the field space.
Okay.
Unfortunately, because the nearest grounds are to the right of the power connections, it's in that space. So if you
Okay.
put power vias in the strip along the power conductor between the to the left of where your cursor is, the left.
Yeah.
So this power bus here,
Yeah.
if you put vias in there and then ground vias next to it, then the field would go in the space between those power vias and the ground vias up to the dielectric between 1 and 2.
Okay.
And the same thing to the right on that. You would put power vias in a strip down through that power bus and put ground vias next to it. And then that would take the energy again from between layers 3 and 4 up to the space between layers 1 and 2.
Okay. So if I'm getting you right, that means I have to line up some ground vias by
Yeah,
this.
yeah.
Okay. Okay.
Just to the
Okay.
side of it, because you don't need a lot. You're not pulling, there's not a whole lot of current at 12 volts.
Okay.
Your higher current is at 5 volts because that's you're using to drive your motors.
Yeah.
So it's, you know, you maybe need, because the voltage is coulombs per cubic centimeter. So
Okay.
at 12 volts, you've got a whole lot more coulombs per wave cycle in that space. And then when you start to remove all this power flood that's everywhere and start to open this up, you're going to have more routing space too. So what I would
Yeah.
suggest is that we do another pass at this, and we
Okay.
record that as well. And what I want to do is then we'll discuss uh, your interpretation of these new guidelines that you're going to create,
Okay.
and we do a couple iterations, and then you can go to fab and build some boards.
Sure. 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 That'll be awesome. That'll be awesome.
So I think that we've got a lot here for you to digest. And
Yeah.
again, you know, what I've been picking is some places where there's an easy to see correction in the design, and take those philosophies and go over the whole board and see where the same type of situation might exist,
Okay.
and apply those across the entire design.
All right.
And you'll get much closer to having what I would call the ideal implementation of this application.
Okay, that's great. One last thing. I actually have the intention of having my stack up as ground, power signal, ground. I think I got the idea from one of Rick Hartley's video. But then the other side is, if I do that, I can't troubleshoot. So
Yeah, I don't always agree with what Rick talks about, which is one of the beauties of our relationship. For this board, and I know but you've already have a solid circuit design. So
yeah, okay,
we're planning to use 1 and 3 as your primary signal routing
okay,
layers.
okay,
Again, because then you reduce the number of ground vias required.
okay,
Because the dielectrics between 1 and 2 and 2 and 3 are automatically connected. It's a paired dielectric design.
okay,
So you would use signal, the top layer would be signal components and power routing.
okay,
The second layer would be ground. The third layer would be signal and power routing.
okay,
And both 1 and 3 would be ground flooded. And then layer 4 would be signal and power components. But that's an orphan layer. So it's a single layer board. And as you are developing this, where you want to take advantage of parallel dielectrics is you would make sure that under these the signal connections on 4 is that there would be ground flood in the spaces on 3 that you're not using to do anything.
okay, 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 great. Great.
and see how that works, and then we'll do another review in a week or so, or whenever you get a chance to work on this. I know you have other projects that you're working on, but so
I'll do it as fast as possible. I think next week will be okay. Next week will be okay.
okay. So this is what I was hoping we'd be able to do, and hopefully you are able to understand the reasons for the changes I'm suggesting. And
Yeah.
then if you have questions about implementation, we can do that outside of this recording. And
Okay.
I thank you for the opportunity to spread Ralph Morrison's teachings.
Oh, the honor is mine. Wow. Wow. Great.
So I'm going to stop the recording now.
Okay, sir.